As a motivating example, consider the riser portion of a circulating fluidized bed reactor. In these systems, clusters are generated spontaneously due to unsteadiness in the flow, and interaction between clusters and the gas phase have been shown to demix the carrier phase in fluidized beds. Because of this demixing, there's reduced contact between the phases, which impedes thermochemical conversion. Because of this, we are particularly interested in the heat transfer that occurs in these types of systems. To date, simple Euler-Euler models for temperature are commonly used to inform reactor design. An example of one of these models is shown here, developed by our colleagues at Iowa State University. An instance of one of the solutions of this system of equations is shown here, where the fluid phase in blue starts off initially warmer than the particle phase in red. Over some thermal development length, L sub T, the fluid and the particles reach thermal equilibrium. But these models neglect important multi-phase effects like clustering because they assume a uniform distribution of particles and perfect mixing. When this is not the case, as shown here, where clusters start off cooler than the gas phase initially in white, you can see that in regions devoid of particles, the cooling of the gas phase occurs much more slowly than in regions that are very close to dense clusters. So in this talk, we aim to answer, how does clustering affect thermal development length, and can we develop improved coarse-grained models that incorporate these effects? To do this, we conduct a novel two-step approach in which we first conduct an isothermal simulation where particles are initially randomly distributed and the gas phase is quiescent. The gravitational body force leads to spontaneous clustering in the particle phase, and then two-way coupling between the phases induces turbulence in the gas phase. This isothermal flow can be characterized by a small set of non-dimensional numbers, including the particle Reynolds number, which is a Reynolds number defined using the terminal velocity of a lone particle in an equivalent flow, defined as the particle response time times gravity, as well as the particle diameter. Another important parameter to characterize the flow is the particle volume fraction, and then the mass loading. After a stationary state is reached in the isothermal flow, the mean velocities are removed from both phases. A temperature difference between the phases is imposed, and a bulk velocity U sub B is added to the fluctuating velocity data. Then an injection velocity of the particles is assigned in order to preserve the mean slip between the phases, and gravity is also adjusted in order to maintain this slip. Then this data is fed into a thermal domain, which is initially just a hot quiescent gas. These particles and velocity fields are injected into this domain until a thermal steady state is reached. The thermal flow, however, is characterized by the same three parameters as the isothermal simulation, along with two additional parameters: the Prandtl number, defined as the ratio of momentum to thermal diffusivity, and a Peclet number, defined by the bulk fluid velocity, the particle diameter, and the fluid phase thermal diffusivity. Both of these simulations are solved using NGA, which is an in-house finite volume DNS LES code that conserves mass, momentum, and kinetic energy, as shown here. Particles are tracked in a Lagrangian manner using Newton's second law, where the right-hand side of the momentum equation includes an interphase force, a force of collision, which is modeled using a soft sphere collisional model, and then the body force. Interphase exchange is handled using a two-step filtering approach, where data is sent from particles to neighboring grid points, and then this solution is diffused with a characteristic size delta F. Here in the heat exchange term, we use the Sun model to inform the Nusselt number correlation. So for this configuration under study, it is 1D in the streamwise direction. And first we take the phase average of the heat equation, where time and spatial averages are denoted by angled brackets. Phase averages are denoted with a tilde, which is defined as the quantity times the volume fraction, then the time and spatial average of that divided by the time and spatial average of the volume fraction itself. Further fluctuations from mean quantities are denoted with primes. And so you can see here that when we take the phase average of the thermal equation, we end up with 6 terms. And we want to assess which of these terms are most important and require closure effort. But first, let's consider a temporally 1D heat transfer problem. So here we have our isothermal simulation, but once this reaches a statistically steady state, rather than injecting the fluid and the particles into a thermal domain to evolve spatially, heat transfer is enabled between the phases, and then over time, it reaches a thermally steady state. So here the flow is homogeneous in all 3 directions, and the evolution of temperature is 1D in time rather than in space. In this study, we find that clustering results in up to a 4-fold delay in heat transfer when compared to a uniform distribution of particles. And that's shown in this plot here, where the vertical axis represents the time that it takes the clustered configuration to reach 99% of the steady state temperature compared to the uniform case. The horizontal axis is the Prandtl number, which I mentioned before is the ratio of momentum and thermal diffusivities. And so you can see here that ignoring multi-phase effects has important industrial implications. Imagine if you designed a reactor to be optimal, but it turned out you had a factor of 4 error in your thermal development length. So what derives these differences? So for the temporally evolving heat transfer, the phased average thermal equation is shown here with 5 terms. And the non-dimensional temperature theta is defined like this. So if we compare the uniform case with a clustered case, you can see that term 1 describes the behavior of the uniform distribution of particles, and it is closed because it consists all of mean quantities. Term 3, however, is important for the clustered flows and is unclosed, specifically this term here, which represents the fluid temperature seen by the particles. So by analogy, we would expect that the following terms will also dominate the heat transfer in the spatially 1D case. So if we compare the important terms from our temporally 1D equation with those in the spatially 1D equation, we would expect for term 3 and term 5 to also be important. But the analogy between temporally and spatially evolving heat transfer breaks down because there's a presence of a bulk gas flow. So to illustrate this, recall the Euler model for spatially evolving heat transfer shown here. And you can see that the bulk fluid flow appears here and the particle velocity appears here. So if we look at realizations of these ODEs that maintains the same slip between the phases but have a different bulk fluid flow or a different Peclet number, we can see that the thermal length and the thermal behavior of each of these systems is quite drastically different. So because we can't directly inform a spatially 1D model from the temporal 1D study, our future work includes simulating the spatially evolving flow using the 2-step approach that I explained earlier, while varying bulk fluid flow and the particle volume fraction, assessing the relative importance of each of the temperature transport terms, and then developing coarse-grained models that take into account multi-phase effects. And to do this, we will use a sparse regression-based method in which it's postulated that the quantity of interest that we seek to model can be described using a linear combination of coefficients and test functions, beta and t respectively, and we can find the ideal set of coefficients by solving the following optimization problem, where this first term is an L2 norm, which regresses the coefficients to the data. And then the second term is an L1 norm to induce sparsity and thereby effectively conducts model selection by setting some of the coefficients to 0 with increasing the tuning parameter lambda. And with that, I would be happy to take any questions during the virtual Q&A session.